Hey everybody, welcome to College Algebra. This is Math 35 at College of the Sequoias. And today we're going to look at functions and what they mean, what they are. This is 2.3 in our book. And functions have very specific requirements that make them useful. And they're not necessarily equations. And the way it works is for every input value, it's like a machine. It's like a machine. We input one thing and the output is something else. And for every input, there's one output. There's exactly one output for a function. When we're working in mathematics, we tend to use x as our input. So if we have x, y, this tends to correlate to x equals input, y equals output. They call this the independent variable because it doesn't depend on anything. It's our input. And since y depends on what value x is, this is the dependent variable. And so for functions, every x leads to only one y value. And this can be very, very useful. This means we won't have two different outcomes. Or more outcomes, which makes it reliable. I know if I stick in a number, whatever number I get out is the correct number. If it's got more than one output and I stick in the number, do I get the output I want? I don't know. So that's the idea of a function. Like I said, it does not have to be an equation. Spreadsheets do these a lot. So an example that's not an equation. Let's say I have Miguel, and he's 21 years old. I have Daniel, and he's 17. Louis is 18. I have Tessa, she's 17. And Francisco is 23. This is a function where names are the input and age is the output. It doesn't work the other way. I can't go the other direction. y. If I put in 17 as age, I could get Daniel or Tessa. And we don't like that. So functions are one input, one output. So if we put in age and get our name, this is not a function. Okay. And so we can look at number sets. Let's take a look at this. Is this function or no function? I can have, so my first set of numbers, I've got -4, 0. I've got -3, 1. And I've got 3, 1. So for each input, I've got -4 input, -3 input, 3 input. I only have one output. This is a function. Even though the output gets repeated, like age up here got repeated, outputs can be repeated, so this is a function. I could have something like set n. N is the points 2, 3. I got another ordered pair 3, 2. I can have another ordered pair 4, 5. And I can have another ordered pair 5, 4. This is not an equation, it's just a set of points. This is a function also. Each input has only one output. The number switching around is fine. 2, 3, 3, 2 are different points. And then we could look at set P. -4, 3, 0, 6, 2, 8, 1, 4, 0, 5. Point or set P has got 5 points. This is not a function because x equals 0 leads to two y's, y equals 6 or y equals 5. We don't like that. No bueno. All right. So when we have equations, we can distinguish which ones are functions by solving for y and replacing y with f parentheses x. F parentheses x most commonly is read as f of x. Sometimes you might hear f at x, but that's less common. Most people say f of x. And y equals f of x says y is a function of x. Okay? F of x, like this, is not is not f times x. F is the name of the function. What's in the parentheses is the input. You might also see f evaluated at x. That's another way of looking at it. It's a little clearer on what we're doing. If I have a number plugged in, then I'm evaluating that function where x equals that number. All right. So if we look at all the possible input values, they have a name for that. The domain is the set of all possible input values. And what I mean by that is legal values that work. I can't use negative numbers for age. So if I'm looking at age, the domain of a function of age requires x to be, well, even having 0 doesn't make much sense. An age of 0 means you're just not born. Requires x to be greater than 0. If we have all real numbers, if any real number works, if any real number works, or x is in the set R, the domain is, we tend to write it in interval notation, negative infinity to infinity. All right. That was all the input values. The output values are called the range. So for like an example, if this is my x-axis and y-axis, let's say that is x equals, or y equals 1 right there. This is x equals 2. If I draw a horizontal line, the horizontal line has a domain of all real numbers. It can be any number, but the range is only one value. It's 1. Or 1, 1. Starts at 1, ends at 1 kind of thing. Most people don't do that. If I had a vertical line, well, now the domain is fixed. It's only got one input value. X is 2. But the range can be any value. Goes to negative infinity to positive infinity. And any other line that's not horizontal or vertical, like a straight line at an angle, a tilt, this has a domain and range of negative infinity to infinity. On the red line, the one I did first, I have an infinite number of input values, only one output value. That's fine. I can have the same input value or output value for multiple input values. This one's fine. The vertical line, though, if I plug in 2, I get an infinite number of outputs. So the vertical line is not a function. I have a single input for an infinite number of outputs. This is not a function. All other lines can be written as a function. And the way we indicate something as a function is if the line is y equals 4x minus 3, we indicate it's a function by saying we replace y with f of x. F of x equals 4x minus 3. When this gets evaluated, when you see something like this, if I have f2 like that, what this is saying is use the function f where x equals 2. And if I use that function there, this is, I'm replacing the x with 2. And I get f of 2 is 4 times 2 is 8 minus 3 is 5. F of 2 is 5. If I do f of 3, 4 times 3 minus 3 is 9. So I have f of 3 equals 9. You can convert this to ordered pairs or coordinates by using what's inside as x values and what it evaluates to as the y value. Okay? So I said vertical lines have a single input and an infinite number of outputs. They're not a function. Every other line can be written as a function. We have a test for a graph. So if you have a graph and want to test for a function, you see if it's a function. We use the vertical line test. And what we do is with the graph drawn or shown, slide a vertical line or ruler, a ruler is a good one to use, from left to right, if at each point it only crosses the graph once, it only crosses the graph once, it is a function. If it crosses more than once, it's not a function. Circle a radius 1 right here. So this is -2, 3 is the center. So x plus 2 squared plus y minus 3 squared equals 1. This is going to be some sort of cubic function because it goes up or it turns twice. I didn't actually give it values or anything like that, something like that. This is what I mean by doing a vertical line test. Looking at the left side of it, the ruler, as I slide the ruler to the right, notice it's only crossing my graph once. I didn't draw in the axes. That's x, this is y. It only crosses the graph once on the x cubed function, or x cubed graph, it's a function. When I get to if I do the circle, the very left side of the circle is only hitting once, and the very right side of the circle is only hitting once, but everywhere in the middle, it hits the graph more than once. So this is a function. Circles are not a function. Okay? And so what violates it is crosses more than once. And over here, vertical lines only cross once. Okay? So we talked about lines. Vertical lines are not a function, but horizontal lines and other lines are. The absolute value graph, y equals the absolute value of x. You plug in different values for x, it doesn't matter if it's positive or negative, it spits out a positive number. The absolute value graph looks like this. This passes the vertical line test. It's a function. If I do the other way around, the absolute value of x or absolute value of y equals x. If I stick in negative values for y, I get positive x. And if I stick in positive values for y, I get positive x. The absolute value of y equals x gives you a graph that looks like this. That part's the same, but now it's like that. This fails the vertical line test, so it's not a function. Okay. Let's look at two other things. I'm going to use straight lines to illustrate the next idea. So a line that goes up from left to right. Going from left to right. These are functions that are increasing. The function is increasing, we call it an increasing function. If it goes down as it goes left to right, this is a decreasing function. So here's like an x cubed graph. And I deliberately broke it up into regions. From negative infinity all the way up to -2, it's increasing. And from 3 to infinity, it's increasing. So our cube function, and this one is for the one drawn. The function is increasing from negative infinity to -2 and 3 to infinity. And from 2 to 3, it's going, or -2 down to 3, this region right here, it's decreasing. It's going downhill. So a function can have increasing regions and decreasing regions, okay? If it's always increasing, we say it's an increasing function. If it's always decreasing, we say it's a decreasing function. But if it switches back and forth like this one, we can't say it's either one. It's just an increasing or decreasing function. That's it for 2.3. That's all that's really going on in 2.3. I'll get 2.4 done in a little bit. Peace.